Alrighty, well, greetings and good evening, minions. I am, as always, Nathan. I am a PhD student in chemistry and an enormous nerd, sufficiently big nerd to do this when I'm not being paid to do it. I just enjoy talking about chemistry and science, and this stuff all makes me very happy. So, yeah, hope everybody's having a very happy Tuesday. I came across a paper today that I gave just a quick little read to. But it was a fairly interesting one. They're working on essentially a liquid battery storing electric potential in in chemical form. In that they take a bulk solution of acetone and they use a couple of it's a multi-component catalyst that works together in a system to hydrogenate the acetone, so turning it from acetone into isopropanol, which can be quite tricky to do, but they were able to do it quite efficiently. Well, not just quite efficiently. They were able to do it extremely efficiently. I think their current efficiency was something. It was above 90%. I think it was 93%, which is truly staggering. What that is a measure of is that essentially saying 93% of the power that they put into this to apply the electric potential to drive this reaction cycle, 93% of that energy is stored in the chemical bonds. So like not very much of this is lost to heat or to extraneous processes, and this is really very unusual in these kind of electrocatalytic systems. They didn't cite any other specific ones, and I haven't looked it up because this is about all of half an hour ago or so that I finished going over this paper. But the normal efficiency of these kinds of electrosynthetic or electrocatalytic systems is perilously low, and has really inhibited a lot of advancement in this field because it just hasn't been efficient enough to be practical. But their system was insanely efficient. 93% is absolutely fabulous. Kind of for most storage systems, that's a very good rate of efficiency, rate of conversion. Because if you think of even other battery systems, just the flow of current in these things is generating some heat, at least. For things like lithium batteries, I think it's really quite efficient, which is why it's the standard. But for a lot of other processes, like even if you think of it's like these kind of gravity battery things where they like lift up rocks, or they pump water up to a high level using the electricity that they're kind of like excess electricity for whatever process they're using to put these heavy objects or the water up on a high level, and then they release it down and spin a turbine or a flywheel and generate electricity that way. Those processes are so much less efficient than this one, because there's all the friction of the working parts. There's other sources of loss too. So it's an interesting interesting little paper. I quite enjoyed it. It was a pretty short little read. Not that I read all of it, mind you, but I skimmed it pretty good. But yes, that was just a very recent 2024 paper in the Journal of the American Chemical Society. So quite a reputable, um, journal as well. So yeah, I thought that was kind of fun. Um, it is a neat idea. And hello, hi. Yeah, so it was quite cool. And yeah, one of the pieces of their catalytic system, one of the co-catalysts, one could say, is called cobaltocene. And cobaltocene is a quite common chemical. It's used in electrochemistry in two capacities, really. In one capacity, it is a fairly mild reducing agent. So something that likes to impart an electron to some other system that is willing to receive it. So in that case, it reduces this other compound and is itself oxidized. That makes it a reducing agent. Yeah, so cobaltocene is used to do these one electron reductions in relatively mild conditions, and its other use is as an electrochemical standard. So it's just something that you use to calibrate your scale of saying, like, this is 0 volts at this process. And so cobaltocene has been used for that for quite a long time, and it is used as a standard because it has very fast kinetics of electron transfers to and from cobaltocene, which gives it a high degree of it's called just electrochemical reversibility. So just the basically what that means is it is a fast and straightforward process for this compound cobaltocene to give up or receive an electron in that process, which is kind of a good starting point for criteria for looking for electrocatalysts, which is what these folks did, and it was great. So yeah, good science. They did a good job. Alrighty. So with that out of the way, I'm going to do just a little bit of chemistry with you tonight. So let's go over here. I apologize, that's very sudden. I need to get my transitions set up again, because I had to switch to new streaming software because Twitch discontinued their support for the Twitch studio. So what a pain. But anyways, that is quite all right. So first question here is talking about the is wanting the approximate pKa values for protons A and B. And so pKa is just a measure of the basically the willingness to give up a proton. So things with low pKa's give up their hydrogens easier. You tend to find that things with low pKa's are the more acidic ones, the ones that prefer to donate a hydrogen. And as you may suspect, things with a higher pKa are less willing to part with their hydrogen. These are the more basic things. They do not want to give up a hydrogen. if they have a high pKa. So when it is asking for a pKa value for a specific proton, so in this case, proton A is attached to a nitrogen. I'm going to make that a little bigger up here for you. So proton A is just bonded to a nitrogen, and so the pKa value for that proton is going to be kind of a measure of how easy is it to pull that hydrogen away from the nitrogen. Okay, so we'll look at both of these kind of at the same time. So A is the hydrogen on an amine, and B is a hydrogen that is attached to an alkene. Yeah, that's kind of its only distinguishing feature. pKa values. We'll just kind of go over a couple just to give a bit of scale. So the pKa of water, so just H2O, is 14. So with a pKa of 14, you get something with the acidity of water, which is to say, not very. Water's not terrible at being an acid, though. And so this would be talking about like this kind of reaction. So going from H2O to H plus OH minus. So yeah, this is this reaction here is the rate of that reaction is kind of governed by the pKa, and I really should. Let's draw the correct arrows here, because this is always going to be an equilibrium. So yeah, the pKa describes the reaction in this direction. Yeah, so water is about 14. So that's what we would probably think of as not very acidic, considering that I'm willing to drink a whole bunch of this every day. Yeah, so 14, not very acidic, not very basic. I hit a button, and that was later regarded to be a poor idea. Okay. Other pKa's that are kind of relevant. pKa of that's a big one. H3O plus. So this is a hydronium ion. This is kind of the measure of this is, what would I say? H3O is kind of the dividing line of what makes a strong acid. So it's basically just protonated water. It's water that has usually just reacted with some other acid, a strong acid usually, so H3O plus is the protonated version of water. It has a pKa of 0, and so in other terms, things that have a pKa above 0 are considered weak acids, which is to say they will not fully dissociate in water. And things with a pKa of less than 0, because you can have negative pKa's, that is totally fine. But things with a negative pKa are always considered strong acids, and those will always fully dissociate in water. And so here's what I mean by that. So if we have for example, hydrochloric acid in water, those will fully react to make so hydrochloric acid in water will produce hydronium, that H3O plus, and a chloride ion. And in this case, I've drawn the arrow with just one head. It is this essentially, it goes to completion. And the reason for that is that when we're talking about things being acidic or basic, there's like talking about one compound and saying this is acidic, kind of, it's not a complete thought, because acidity and basicity are relative measures. So like H3O is acidic with respect to water, because its pKa is lower than water, so it is more acidic compared to water. But H3O is basic relative to HCl. HCl, it has a pKa of around, I think, -4, maybe -5. And keep in mind, these pKa's, these are values that are given on a logarithmic scale. So for every integer, that is an order of magnitude. So when we have H3O plus at pKa 0 versus HCl at -4, that's 4 orders of magnitude, which is to say that HCl is 10,000 times more acidic than H3O plus. This is not the neatest writing I've ever done, but I hope you'll forgive that. Then H3O plus. So yeah, it's not just a little bit more acidic than H3O plus. It's a lot more acidic. So when we have this reaction, okay, technically there is an equilibrium arrow there going the other way, but it's like I can't make a mark small enough to illustrate how minor that reversibility is. And so for all intents and purposes, to an analytical degree, this goes to 100% completion. And all you have in this solution is H3O plus and Cl minus. So yeah, and so that's a strong acid. So strong acids fully dissociate in water. They make 100. They go to 100% to completion, making H3O plus and whatever counter ion. Because there's also things like sulfuric acid, which would be like H2SO4 plus H2O going to H3O plus HSO. Ooh. 4 minus. Yeah, so sulfuric acid is another acid, very strong acid. I believe it's about -10 or so on the pKa scale. So yeah, sulfuric acid is ridiculously acidic. It's fairly nasty. I don't super enjoy working with it. Like, it's fine, but I have accidentally burnt a hole clean through a lab coat just by getting a drop of concentrated sulfuric acid on it and not realizing that. Yeah, it was a little bit wild, but that's fine. So yeah, strong acids will fully dissociate into their conjugate base. HSO4 minus is the conjugate base of H2SO4. Cl minus is the conjugate base of HCl. However, if you have a weak acid, take for example H3CCOOH. This is otherwise known as acetic acid, or vinegar if you prefer. So vinegar is okay, let's put it up here. COOH. pKa of acetic acid is round about 5. So it's more acidic than water. Like water's up at 14. Acetic acid's at 5. So it's significantly more acidic than water, but it's not as acidic as H3O plus. So when we go through this reaction with acetic acid, what we form is H3O plus H3CCOO minus. So we're still producing H3O plus here. And H3CCOL minus, the conjugate base of acetic acid. It's called acetate. But when we do this, and so here's where the pKa's become important. So I'm just going to write above each of the acids, minus 10, 0. I'm just going to write their pKa's. And we're just going to assume that I have remembered these perfectly, because that's fine. 5 and also 0. Okay. So when we go through this reaction with a strong acid, then we can't really go backwards to any significant degree. Like the amount that we would do the reverse reaction, like H3O plus acting as an acid and protonating HSO4 minus, the amount of times that would happen is negligible, completely negligible, because H3O plus is so much less acidic than than sulfuric acid, right? Because this is 10 units on the pKa scale, which means it is 10 orders of magnitude, which is 10 billion times. Sulfuric acid is 10 billion times more acidic than H3O plus. So you might have like one part in 10 billion in this solution that goes in that direction. But that's just not enough to consider for any sort of practical application. So for all intents and purposes, this is all that you have. H3O plus is just not a strong enough acid to protonate HSO4 minus. Same thing with hydronium and chloride. It's not a strong enough acid to produce hydrochloric acid. But in this one, in the case of acetic acid, the hydronium is about 100,000 times more acidic than acetic acid. And so when you do go through this reaction with acetic acid and water to produce hydronium and acetate, the hydronium is very keen to protonate the acetate back to acetic acid. And I'm just going to redraw these a little bit for a bit of context. So I'm just going to draw a short little arrow there and a long arrow there. So in fact, this reaction favors the starting materials quite strongly, in fact. Now, what this means in practice is that when you have vinegar in water, you'll have a small amount of hydronium and acetate in that solution, but mostly what you'll have is the unaltered acetic acid and water. And that's because the hydronium is so much more acidic than the acetic acid is. And this plays into another principle that we come up against fairly often in, well, not just organic chemistry, I suppose, but in several areas, that when you have equilibrium, which is, most of the time, technically, but we don't know where that sentence is going. Let's try again. So when you have a reaction at equilibrium, the equilibrium favors the side of the reaction with the weaker acid. And so you'll see that in each of these cases. In the reaction with sulfuric acid, hydronium is the weaker acid, so equilibrium favors the product side. And because it's so much weaker of an acid, this equilibrium favors the product side to an absurd extent, to where we don't even consider the reverse reaction particularly. And same for the hydrochloric acid. This is still very, very product favored. And then when we get to the acetic acid, the weaker acid is on the reactant side, or the starting material side. And so this reaction is significantly favors starting materials. So, all that to explain kind of what pKa is and have a couple little guideposts as to what pKa's look like. So when we're looking at these two, at hydrogen A and hydrogen B, this is this is something that we have tables for. This is not something that you should just try to memorize for the sake of knowing it, because knowing the specific pKa of a specific compound is not that useful. Like I said, this is why we have tables. This is why we have data tables. That being said, I have known professors who will have questions like this on an exam, and they will refuse to supply a table of pKa values. And so in those cases, for those professors, some memorization is necessary. This is a practice that I object to very strongly, because it is worthless memorization. Memorizing a bunch of pKa values does not make you a better chemist. It has essentially no value at all. And that is exclusively because we have data for this. And there's no there's very little you can do to build up procedural knowledge to figure out what the pKa of something is. So there's no practical use in memorizing it. It's just something that you'll pick up over time, unless your professor is unless your professor's a dickhead and wants you to memorize stuff for no good reason whatsoever. So, with that being said, now I have never gone to any great lengths to memorize pKa values, but I have seen them enough that I've picked a few up, and I'm not too bad. at least guessing pretty closely what it should be. A hydrogen attached to a nitrogen, which is an amino hydrogen, is roughly in the 30 to 40 range. So my of our options here, 10, 25, and 35. This is pretty certainly either C or E. Because yeah, 10 would be more acidic than water. This is very, very not more acidic than water. 25. Oh hell, I don't know what would be around 25. Look up a table of pKa values, and you can tell me. But an amine is going to be around 35. In most cases, there can be other effects, like you can look at the structure and see some resonance effects, or some very electronegative atoms in proximity to stabilize the resulting negative charge. So there are certain cues you can get from the rest of the molecule. But just as a first approximation, your best bet here is going to be 35. So for B, alkanes and alkenes are much more basic. They're less acidic, I should say. It's much harder to remove a hydrogen that is bonded to a carbon than it is to a nitrogen, and that puts us at our options are 25, 44, or 50. I don't know if I've seen anything with a pKa of 50. I probably have, but it's pretty extreme. And if memory serves, which I'm pretty sure it does, a typical value for an alkane or an alkene would be about 44. So this answer is C. All right. All right. I'm pretty sure I spent about 15-20 minutes on that test. This is a multiple choice. I hope it wouldn't take that long on an exam. Don't worry about it. It's fine. We talked about a lot about this stuff. So that's just streaming efficiency. That way I don't need many of these problem sets, because I can just talk about them for a while. And that's fun anyways. So, what is a condensed formula for the structure below? So a condensed formula is basically it's a chemical formula with structural information encoded into it. So, for example, when I wrote out the formula for acetic acid, I wrote out H3CCOOH. And this is a condensed formula. I might call it a condensed structural formula, but it's potato. So there is structural information encoded into this formula, and I'll show you how I do that. Because the other way that you could write this formula would be C2H4O2. And this is also correct. This is also the formula for acetic acid. But this has no structural information in it. You could come up with multiple rational structures from this formula, and it gives no indication of which one would be correct, and those are called isomers. We've done some of that previously, and they're terribly fun. I really like the kinds of questions that give you a formula and says, hey, make a bunch of isomers of these. The most extensive one of those that I think I've seen was I'm trying to remember. They gave us one in, was it advanced OChem? This was like organic chemistry 3 or advanced OChem or whatever, and we got a formula that had, I think, about 20 or so isomers that you could reasonably draw from it. I think it's pretty fun. It's a little like open-ended puzzle that I kind of enjoy. But anyways, that is a bit of a diversion. So when we're making a structural formula out of this, we kind of start at one end and go to the other, and it describes the structure along the way. So, for example, let's start with this. So the first group that we see is H3C, because hydrogens can only support one bond. So if you see H3 like this, it doesn't. It is not saying that you have H to H to H. That would be scary, absurd, all of these things. But yeah, this is not what they mean by H3, because that can't be right, because this hydrogen, it cannot support two bonds. Hydrogens cannot carry 4 electrons with them. So what this is referring to, when it's combined with the next letter, because you can also do things like H2N, COCH3. I'll do that one in a bit. Yeah, so if you did something like that, if you start with H's, then look at the next element, and it's probably connected to those. So getting back to this one, we got HC. Yeah, so it's just describing a methyl group. The next atom that we've got is a carbon, and so with the methyl group here, all of the hydrogens have one bond already, so they're full. We can't connect anything else to them. But carbons need 4 bonds. One of my professors like to tell us that there's few things that are certain in life: death, taxes, and 4 bonds to carbon. And so we've only got 3 in this carbon, so we're just gonna draw a line to that next carbon. And well, that's kind of it. So now we get to the next atom, which is an oxygen. And of course we have nowhere else to put it except for this carbon. And so we'll put it there. So this is where this particular compound gets a little bit tricky, and one might suggest this wasn't the best molecule to start on, but that's okay. We're going to ignore that and press on. So when we've got this kind of a situation, so we've got our oxygen here. The next atom is also an oxygen. And so we could envision a couple ways that we could construct this molecule. We could just kind of keep going over this way and bond the oxygen to an oxygen. And if that looks terrible to you, good, it should. Because this is a peroxide, and peroxides are hideously reactive and gross, and we don't assume that they are part of our structure unless we have a very good reason to think that they are part of our structure, because it takes some fairly extreme, well, I don't know if I want to call it extreme reaction conditions, but some pretty harsh reaction conditions are required to make a peroxide. And peroxides themselves are very seldom stable to any appreciable degree. We have things like hydrogen peroxide, which breaks down over time. You know, if you get hydrogen peroxide in a bottle from the pharmacy, first of all, hydrogen peroxide is always kept in an opaque container. So usually like that brown plastic container or a black plastic, but it's never glass. Because if it is, if peroxides are exposed to sunlight, they react with stuff and they break down. It's yeah, which feeds into like the peroxides are just not very stable compounds, and so you like if you want them to be to stay together for any kind of long term storage, you have to store them very carefully and preferably cold. But but the other thing about this that is a tip off that this is not the right structure is that like if we went down this way, we could put the hydrogen on the end of here, and now oxygen wants 2 bonds, hydrogen wants 1 bond, and carbon wants 4 bonds. That means everything in this is fine except for this carbon, which only has 2 bonds to it. And so that carbon is breaking rules right now. And we don't like that. And if we're just like drawing a structure from a formula, we don't do stuff like this because this simply wouldn't exist. And if it existed transiently, it would be extraordinarily reactive and would immediately be something else. So for this reason, we don't connect the oxygens. We put the second oxygen on the carbon as well. Now, that gives us essentially 2 options of where to put the hydrogen. We could put the hydrogen on the carbon, just so that the carbon has 4 bonds, and that's what we prefer. We like that just fine. But that then breaks rules for the oxygens, because remember, oxygens want 2 bonds. And if they don't have that, they're not very happy oxygens. All right. So the solution is that we have to give one of the oxygens a hydrogen, and we have to give the other oxygen a double bond. Because usually double bonds will not be specified in condensed formulae. It is generally left up to the student or the chemist to infer the presence of double bonds based on the kind of heuristics that I just kind of laid down for this one, just which is basically the directive to just like make sure that carbons have 4 bonds, oxygens have 2, hydrogens have 1, and so this is really the only configuration that's possible for this molecule if we are determinedly avoiding terrible options like peroxides or oxygens with 1 bond and stuff like that. So that's how we use condensed formulae. Oh right, I was gonna do these ones too. So this one, start with the nitrogen. It's got 2 hydrogens attached to it, and then it's bonded to a carbon. I should be putting my lone pairs in here. Please don't tell my teachers that I did that. So nitrogen wants 3 bonds, which now it has the 2 hydrogens on the carbon, so that is just lovely. So this one could also go a couple ways. We could go to the oxygen and then to the methyl group, and that doesn't look completely terrible. We're not making peroxides or anything, but once again, we're leaving a carbon with just 2 bonds, and so this is not correct. We have to make a carbonyl out of this group, and then a methyl group over here, and that's how we do that. And it's often going to be the case that when you see a carbon and an oxygen next to each other, it's often a carbonyl, because carbonyls just kind of like to exist. But certainly that's not all the time. Like, you can certainly have things like, what would it be? CH3, CH2, OCH2, CH3. Okay, so this is a formula for diethyl ether, which looks like this. Yeah, so in this case, the oxygen is in fact just all in line, and just has a couple double bonds going. No, it doesn't. I don't know why I said that. That's silly. So it is in the chain along with these carbons, and kind of the tip off to that is that it's flanked by these CH2 groups. And so a CH2 group like this, let's highlight it in a different color. So it's got the CH2, and then it needs 2 other things to be bonded to. And so it's bonded to the terminal methyl group, and it's bonded to the oxygen. And the only way to rationally do that is to have single bonds to each one. Okay. So, now, getting back to the question that I started quite a long while ago, after hydration. Okay. So, our options are, so again, these generally go left to right, and they've been kind enough, yes, they've been kind enough to draw the structure left to right as well. There's no particular requirement for it to be that way, but it helps. So we got. So in these 2, we start off by saying there's 2 methyl groups, which would be here and here. So that seems fine. Now this one specifies 1 methyl group, so like here, I'll make this in a different color. So it talks about the methyl group, and then the methine group. Methine is just a very seldom used term among chemists for just a CH group, which is this guy. And then in brackets, it's got a CH3, which could indicate that one, which is so far, this isn't the way you would usually see it done, having this in a bracket. It can be, but it's weird that this one hasn't been consistent between just a CH3 group on the end, and then specifying like this. It's a little weird, but not super wrong. Not super wrong. It's I wouldn't call this wrong. I'd call it slightly unusual, but fine. So we'll keep going. There's the CH, which is this guy. Cl, which is here. CH again, which is over here. And then CH, So here's the problem. So it says a CH followed up by 2 methyl groups, but there are in fact 1, 2, 3 methyl groups. So for this to be correct, this would have to be a 3, but it's not, and we're not going to just artificially redeem it. So it ain't. It's not B. Yeah, and so this one starts out with 3 methyl groups and again ends with 3 methyl groups. Now that we're looking out for that, so there's 3 methyl groups on this side, but there's only 2 on this side, which means this one is also wrong. Now it's down to these 2. So this specifies 2 CH3 groups here and here. That's fine. They go on to specify a CH group. That's fine for both. Another CH group. That's here. And then CL. And that's here, of course. Oh, and I just noticed in this one. So this is not a CH group, as I've just realized. Is in fact just a carbon, because this carbon has 4 bonds without any hydrogens being drawn, which means it is just C. There's no H along with it, which means that this here is right, and this is wrong. This one also specifies 2 methyl groups on this end, whereas this one specifies 3. So once again, for the second time in a row, the answer is C. So if in doubt, go with C. Alrighty. Okay, so what is the formal charge on the oxygen atom in the structure below? So formal charge, which I'm going to abbreviate FC because writing is a pain in the butt with a mouse. Formal charge is the valency minus electrons. So the valency is it refers to like the number of electrons that need to be around an atom in order for it to be considered neutral. And so that also corresponds to the number of the group that it's in. I wish I had a periodic table. Do I need it? No, I don't think I need it. And so what this refers to, so for example, carbon is in group 4, nitrogen in group 5, and oxygen is in group 6. And so, how shall I say this in a way that makes sense? Okay, I've got it. So, when we look at a compound, let's take just a very simple compound. So we're just gonna do okay. So we've just got a very poorly drawn methane here. So it's a carbon with single bonds to 4 different hydrogens. So the valency of carbon is 4, which basically means that it needs 4 electrons in its valence shell in order to be considered neutral. Because right, so So carbon's valency is 4. And that doesn't change. That never changes. It's a constant that is specific to whichever element you're talking about. So if we're talking about carbon here, carbon has a valency of 4. It needs 4 electrons in its valence shell to be neutral. And so we subtract from that the number of electrons that are actually around it. Now, there's a specific way that we have to count electrons in order to assign a formal charge. And what that is we take each bond, because each single bond has 2 electrons. And so one way that you can split that up is to say that each bond has 1 electron from each element. From each atom on either end of the bond, because these kind of covalent bonds here are effectively like 2 atoms sharing 2 electrons. So effectively 1 electron for each atom. I should note at this point that there's different ways that we can count electrons in this way if we're trying to find a different value. So right now we're trying to determine formal charge, but like if we were to instead say like we're trying to find the oxidation state. Oxidation states are different in that we count all of the electrons in a bond as belonging to the more electronegative element. So whichever of the 2 atoms in that bond, whichever one is more electronegative gets all of the electrons. And so in a methane like this, carbon is very slightly more electronegative than hydrogen, and so you'd say carbon gets all of these electrons here. But that is oxidation states, and that is a discussion for a different time, because right now we're dealing with formal charge, which is kind of a way to measure like if there's a excess or deficiency of electrons in that molecule and on that atom. There's a ton of caveats that come with assigning formal charges. I'll maybe briefly talk about that in a minute, but for right now, what I want to do is finish doing this. So in the case of methane, looking at formal charge, so we split each of these bonds and we give 1 electron to the hydrogen and 1 to the carbon. And so in this way, carbon receives 4 electrons, because there's 4 single bonds, it gets 1 electron from each, so it gets 4 electrons around it. And that means that the formal charge on this carbon is 4 minus 4, which is, last time I checked, 0. So methane here has no formal charge on carbon. Hydrogen, for example, has a valency of 1. It just has 1 electron in its valence shell. If it has 1 electron in its valence shell, it is a neutral hydrogen atom with a charge of 0. So each of these hydrogens also gets 1 electron from these bonds. So they all have 1 electron and a valency of 1, which means that every atom in this molecule of methane has a formal charge of 0. All right. Actually, I do think that's all I want to say about that. So, now, So we have to find out what is the formal charge on the oxygen atom in the structure below. Oh gosh, I am going to have to talk about that. Okay, that's fine. All right. Excuse me. So. Okay. Okay, so oxygen. So we'll set this up over here. So formal charge equals 6. So 6 is, again, the valency of oxygen. It needs 6 electrons in its valence shell to be considered neutral. So then we have 6 for the valency minus the number of electrons around it. So in this case, this oxygen has 3 bonds to carbon. So if we break each of those, and also the double bond here, it's 2 bonds to the same carbon, yes, but it acts. We're going to treat it exactly the same as we would just 2 single bonds. So we split the whole double bond in half. So there's 2 electrons that come from this double bond, 1 electron from this single bond, and the lone pairs on oxygen are fully localized on the oxygen, and so that counts for 2 as well. So we got 2 from the double bond, 2 from the lone pair, and 1 from the single bond. So that means that we're looking at 5 electrons around this oxygen, which means that it has a formal charge of +1. So this oxygen should have a little plus sign on it. So actually, once again, the answer to the multiple choice question is C. So I guess if you're taking an exam from whoever it is that wrote this, if you're not sure, go with C. Okay, so need to talk a bit about what that formal charge means. So basically what that formal charge indicates is that there is a deficiency of electrons in this molecule as a whole. Right, because so how shall I explain this? Okay, so it's this is not the same as saying that this oxygen is electron deficient, because that would be implying that this oxygen has less than a full octet, and that's simply not correct. Actually, every atom in this molecule has a full octet, right? Because so let's just draw this out fully. Whoop, that's not a carbon. Okay. So, so often when we are drawing molecular structures like this, one thing that we'll often do is we'll like if you start from just kind of like first principles, we look at this molecule and we say like, okay, so how many electrons are in this molecule in total? And so to figure that out, you look at how many valence electrons each of these atoms brings to the molecule. So hydrogen atoms contribute 1 valence electron. Carbon atoms contribute 4, which you may notice is the same value as their valency. It's because we're talking about the exact same thing here. And oxygen would contribute 6. So if we had if we were given a structural formula, like we wouldn't even need to have this structure given to us or anything. If we just had the structural formula of C3H7O, then we would say this has 12 plus 7, 19, should have 25 electrons. Right? Because what we're doing here is we're assuming that each of these elements is neutral, and then we just count up how many valence electrons they bring to the molecule, and then we start to put stuff together. So we can count the electrons that are taken up in bonds and lone pairs. So remember, 2 electrons for each bond. So 2 for a single bond, 4 for a double bond. And the lone pairs here, each of these dots is 1 electron each. So 2 electrons for each lone pair. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bonds. So 11 bonds. So that gives us 22 electrons. And we've got 1 lone pair. For 2 electrons, and this gives us 24. And that, you may notice, is not 25. So, seems a little bit weird, right? So this whole structure has 1 fewer electrons than it kind of should have, and this is why the molecule as a whole has a positive charge. It's missing an electron compared to what it should have based on just the neutral elements. And so when we count up the formal charge of each of these atoms, I'll give a little bit of a spoiler alert. All of the hydrogens have 1, which means that they have a formal charge of 0. All of the carbons have 4 bonds around them, which means that they also have a formal charge of 0. So the oxygen is the only atom that has this positive formal charge. But as I said, all of these atoms have a full octet, a full duet for hydrogens. Hydrogens only need 2 electrons, but they're special. But the carbons and the oxygen, they all have 8 electrons associated with them. They have full octets, right? Because so when this is another way to count electrons, just in case having 2 wasn't confusing enough. So when you're assessing, like, does this atom have a full octet or not? You count just 2 electrons for each bond and 2 electrons for each lone pair. And all of these add up to 8. So the oxygen has 3 bonds and a lone pair. That's 8. All the carbons have 4 bonds. That's also 8. So everybody's got a full octet, but there is a missing electron. And so, in one sense, that formal charge is on the oxygen. But that's not exactly right either, because like I said, like all of these atoms have a full octet, but that charge, it is somewhere, but so the formal charge is not saying that this oxygen is electron deficient. It's just saying that in this molecule there is a deficiency of electrons, and you can but also like the formal charge kind of like localizes where the deficiency is, but it's a little deceptive to put it on the oxygen, and I'll show you why. I kind of want to just nope, not that. Okay, we'll just crap. Well, this hasn't turned out at all, has it? Okay. Let's just try that again. So. Oops, forgot a hydrogen there. Okay. So I've talked about like electrophiles and stuff like that, being just like this region of electron deficiency in a molecule. And when we were talking about that, I said like look out for especially things like positive charges. And I mean, like, I'm not wrong saying that, but as with a lot of chemistry, there's caveats there. So you might be tempted if you had something like a nucleophile, maybe with a negative charge and a lone pair. You might be tempted to just say a nucleophile here would attack the oxygen because we've got an excess of electron density, we've got a deficiency of it, and so that's how it goes together, right? No. No, straight up no. That's not what's going to happen. The number of times, like the number of problems that I've like gone through and solved in my time as a chemistry student, the number of times that I've attacked an oxygen with a nucleophile, it might be 0. It's a good possibility that I have never used a nucleophile to attack an oxygen, and like use an oxygen as an electrophile. It doesn't really happen very much. Only real exception being in diatomic oxygen, where you have this kind of situation where like sort of kind of one of these oxygens acts as an electrophile, but it's a weird radical process. I genuinely just don't count that. So if this is not saying that this oxygen is an electrophile, well then gosh darn, what is our electrophile? And we can get a sense for where the actual electrophile is by drawing a resonance structure. I forgot my hydrogen again. How dare I? Jeez. So if we had, no, not doing the nucleophile because that wouldn't be a resonance structure. But what we've got is a pi bond associated with a pi bond that is connected to a positive charge. And when we've got that situation, we can take the electrons of the pi bond and put them onto the atom with the positive formal charge as a lone pair. And so oxygen gets a second lone pair. And then if we do the same formal charge calculation, we got 1, 2, 3, 4, 5, 6. And so this oxygen becomes neutral. But then this carbon here had electrons taken away from it, right? Because it was associated with those electrons in the double bond, but those got taken away. And so with electrons moving away from it, it has taken on a positive charge. And in this case, now this carbon only has 3 bonds around it. And so that is not just a formal charge, but this is an actual real charge. This is an electron deficient carbon that has only 6 electrons around it, not 8. That we associate with the full octet and a stable element. So in this resonance structure, this is the worst of the 2 resonance structures. So and just a very quick refresher on what resonance structures are. Resonance structures are not different forms that this molecule can switch between. Resonance structures are just different ways to draw a molecule, but all of the resonance structures exist simultaneously on all of the molecules. So like both of these forms of this molecule exist simultaneously. And so the actual molecule can be described as a weighted average of its resonance structures, where the structures are weighted by kind of how good is a structure. Does everybody have an octet? Have we minimized formal charges and different criteria like that? So the less good a resonance structure is, the less it contributes to the form of the molecule. However, this structure is less good than this one because it has an incomplete octet. Everything up here has an octet, and that's kind of the first criteria for is this an okay resonance structure. This one doesn't, and it's not great, but it is very often the worse resonance structure that is more descriptive of the reactivity of a molecule, right? Because the best resonance structure depicts the most stable form of this molecule. And when that form is more stable, it is less reactive. So it is very frequently the worse resonance structures, the less stable resonance structures, that are more reactive and that describe where these actual charges or formal charges, where those are localized. And so in this resonance structure, you can see that this carbon is first of all, this is a carbocation, and it's extremely reactive. But because it's extremely reactive, it's the thing that reacts. And if you do an orbital analysis, just using some computational software, you'll see that positive charge is almost completely localized on this carbon. and much less so on the oxygen. So this is the reactive form of the molecule, and this is the better description of where that charge is localized, like where that not whatever's the opposite of an extra, where that lack of an electron is most localized. So, but now if you're just drawing it out for giggles here, you would probably draw it like this, and then if you have a nucleophile come and attack this this molecule, again, like I said, I don't think I have ever used an oxygen as an electrophile, even when that oxygen has a positive formal charge, because it's always the thing next to the oxygen that is the actual electrophile here. So the nucleophile will form a bond with that carbon, and because we cannot have 5 bonds to carbon at any time, we have to break one of its bonds, and the easiest one to do that with is the second bond of the double bond, the pi bond. And those electrons just shuffle over to the oxygen to give it a formal charge of 0. Yeah. All right. So, that, I think, is where I'm going to leave it today. Yeah, because I'm tired, and I've been talking for, just about an hour and a half. Turns out that's work. So, I hope that you all have a lovely week. I've had to decrease the number of streams that I do for the next little bit because I'm just kind of ridiculously busy and just haven't had time or brain space to do this twice in a week. But I do plan to still be back next Tuesday, probably. I don't know. Next week is I suspect going to be the busiest of the busy weeks that I'm going to have in the next little while. So we'll just have a little question mark there, but hopefully I will see you next Tuesday. Oh, you have a lovely week, and I hope you had fun, because I did. Okay, bye.